You are welcome to the GMAETS 41's live class section. We'll be dealing with physics in this particular class. So once again, I say welcome. So if you've joined the class, of course, you know you can indicate that you can hear me so that I kick off the class right away. This particular class is going to be focused on preparing our dear students who are going for WAEC and JAM. But of course, those in SS1, SS2 can also benefit from this particular class. Because of course, all of you are tending towards something to sit for that final examination at O level. And of course, take your entrance exam JAM. All right, so if you can hear me, please indicate by typing I can hear so that I'll kick off the class. If you have joined the class, all right, Queen, thank you for indicating. Onyebuchi, thank you for indicating. Adeze, thank you. Sweet, thank you for indicating that you can hear me. And of course, there is no time, we've got to kick off. So what are we looking at in this particular lesson? This class is going to focus on thermal expansion of solids. Thermal expansion of what? Solids. If you're yet to subscribe to this channel, please do well to hit the subscription button. Like I've always advised, turn on the notification bell so that once I kick off any class anytime or I upload any content, a pre-recorded video, you can be personally notified by YouTube. Don't forget, as this class kicks off, you may choose to support GMAETS 41. Like I've always said, I greatly appreciate that. Just besides, the chat box or section, you have the currency icon. You can click on it. And of course, support GMAETS 41 with whatever that is convenient for you. Let us kick off, for there is no time. And I have a good news for you guys after this class with regard to what GMAETS 41 will be doing henceforth. Say 2 days evening, yesterday I was terribly down. Yeah, I was terribly down. If you've been following our classes, you would have agreed to the fact that I've been up and doing, to deliver some courses for the GMAETS 41's students and of course, fans, right? Our family and friends who were taking some courses in the university. So the stress build up took a terrible toll on me. That's why 2 days ago evening, yesterday, I couldn't appear online. But I'm here now, and we are set to kick off. So there are questions that have been sent forward by the GMAETS 41's physical lesson, that's physical JAM lesson student. We have our physical lessons for JAM and WAEC students. And once we are done with any topic, students are tasked. The students are tasked to come up with questions, source for questions, real-time exam question. Of course, I vet them to see that those questions meet standard. And then we deal with this. We have various groups from our physical lessons, okay? JAM and WAEC physical lessons. We have various groups. That these particular questions we are going to deal with, which are based on thermal expansion, were questions provided by Group 1 of the GMAETS 41's physical JAM and WAEC lesson. Now, a brief background before we move on to dealing with these questions. There are 10 questions we're going to look at, right? When you talk about thermal expansion, here you are looking at the ability of usually solid. We are still going to, look at other aspects of heat energy. Usually solid undergoing expansion as a result of, being heated. So if you heat a solid, for example, The solid can expand linearly, that is straight line expansion. The solid can expand both in length and breadth. It's possible, that is length and thickness. If that happens, we can say that the solid has expanded in its area, where we talk about area expansion. Now we can also consider a situation where the solid expands in its length, in its thickness or breadth, and then in its height. There you know the concept of volume comes in. And then we talk about volume or cubic expansivity. So that is what this particular live class is based on. If you know anyone that is sitting for this examination, all right, preparing for work and JAMB, anyone in SS1, 2, right, those in advanced level, because I know there are some schools where there are 100 level students, there are 200 level students, deal with the concept of thermal expansion, can always invite these ones to join the GMAETS 41's classes. No time, this channel is dedicated to giving students the best at all time. Now, I have explained the concept of, thermal expansion, creating expansion in solid as a result of the solid being heated. So we're going to give attention to linear expansivity. We're going to give attention to area expansivity. We'll also talk about volume or cubic expansivity. Now, when you talk about linear expansivity, what are you actually studying? You are interested in the increase in length of a solid per unit length per degree rise in temperature. So there we look at the fractional increase in length per degree rise in temperature. For each degree rise in temperature, what's going to be the fractional increase in the length of that solid when the solid is being heated? That is what we refer to as linear expansivity. It has its formula. As we solve these questions, we're going to see if we have questions drawn from there. Then when we talk about area expansivity, we are looking at a situation where we have a fractional increase in the area of a solid as a result of that solid being heated. For every degree rise in temperature, there is a fractional increase in the area of that solid. To simply define, area expansivity is the increase in area per unit area per degree rise in temperature. But make no mistake, this definition given brings in a concept of fraction. Whether you're talking about linear expansivity, area expansivity, or volume expansivity. As you will see soon, we shall look at situations, when questions are given, you'll be seeing numerator, a change in something. Then the denominator, you have the initial value of that thing in the numerator. So it brings in the concept of fraction, which means when you are talking about linear expansivity or area expansivity, we can also define it as fractional increase in that quantity, whether in length or in area. But remember, this increase is as a result of every degree rise in what? Temperature. Then quickly, I'd like to tell you about volume or cubic expansivity. It is defined as the increase in volume per unit volume per degree rise in temperature. That is, for every degree rise in temperature, if you heat a solid and then the temperature of that solid increases by 1 degree centigrade or 1 Kelvin, right? What is going to be the fractional increase in the volume of that solid? That is what, like I said, we are going to deal with. So without wasting time, we shall pick our very first question as supplied by Group 1 of the GMAETS 41's Physical Jam lesson. Question number 1 reads, you know how we do that? I dictate it and then you can copy as much as possible. So the very first question I have here supplied, a blacksmith heated a metal whose cubic expansivity is 6.3 times 10 to the power of 4 per Kelvin. The real expansivity is A blacksmith heated a metal whose cubic expansivity is 6.3 times 10 to the power of minus 1. The real expansivity is what? So here we are given the cubic expansivity, and then we are asked to find the real expansivity. So in this question, there is a little issue there, right? There's a little issue in this particular question because of the data supplied. It seems like we do not have the complete data in this question. So group 1, I don't know the source of this your question, right? But there is something we're going to do based on the options given. Because let us assume we are in the exam hall. I will definitely go for a particular option here. Now, we are told that a blacksmith heated a metal whose cubic expansivity is 6.3 times 10 to the power of 4 per Kelvin. The real expansivity is what? I'm going to list the options. We're given the cubic expansivity, and this is the symbol we use for cubic expansivity. The cubic expansivity is given as 6.3 times 10 to the power of 4, and then per Kelvin. Option A, what is going to be the real expansivity? Real expansivity, we use this symbol for it. This real expansivity symbol. Option A given to us is 6.3 times 10 to the power of 4 per Kelvin. Option B, let me fix option B here. We're given 4.2 times 10 to the power of 4 per Kelvin. Then option C, we have 2.0 times 10 to the power of 4. We have per Kelvin. Then option D, we have 2.0 times 10 to the power of 4 per Kelvin. I really don't understand how and where this, my dear group 1 students, brought this question from me. I can even see the options C and D being equal. All right. Although group 1, you have penalty to face already because the group violated a setting of the GMAETS 41's rule and principle. I've told you guys on Tuesday you're going to face the penalty because your parents are doing a lot to give you the best. You want to also work hard to make them happy. And of course, as the GMAETS 41 gives you the best, there's no time for you to mess up. Yeah. So this question you brought, like I said, the information there is not complete. It's not complete. Let us assume that I am seated in the examination hall. Two things are involved. If this is the exact question given, right, then you might decide not to select any value. Or per se, if you really wish to select a value, you can go for this same guy. Right? This option A. Saying that, okay, the cubic expansivity being equal to the real expansivity. The reason for that is we can approximate that the apparent expansivity is equal to 0. We can say that. Although if that is the case, I guess the examiner was supposed to have mentioned it in the question. This is my reason for saying that. We know that, recall, cubic expansivity, volume expansivity is equal to real expansivity plus apparent expansivity. Real expansivity plus what? Apparent expansivity. That is what our cubic or volume expansivity is. Now, in the question, we're given the cubic expansivity. We are asked to find the real expansivity. So we're supposed to have been given the apparent expansivity, perhaps. So that to get the real expansivity is going to be cubic expansivity given minus the apparent expansivity. So from here, the real expansivity is going to be the given cubic expansivity or volume expansivity minus apparent expansivity. However, we were not given this value, which makes this question somehow incorrect. Like I said, if I were to be seated in examination hall, I would rather go for option A. Because an assumption can be made that, okay, when the vessel containing whatever is being heated, I think according to the question, all right, we're not told, okay, it's a metal that was being heated. It's a metal. right? So if the metal is being heated, in that case, then we expect that maybe approximately the apparent expansivity is going to be equal to 0, because for the case of apparent expansivity, there it is the increase both in the substance being heated and the liquid contained in it. But since this is a metal, are you following, right? It is a metal. We assume that no liquid is contained, and that is why I am tending towards this option. So I can assume that this is equal to 0. Remember what I said, for there to be apparent expansivity, we expect the metal to contain some liquid. Because by definition, I'm going to tell you this, apparent cubic expansivity. Apparent cubic expansivity is defined as the increase in volume per unit volume per degree rise in temperature for the increase in the volume contained, are you following, or when the liquid is heated in an expansible vessel. When the liquid is heated in what? In an expansible vessel. I repeat that definition again. Apparent cubic expansivity, which is this guy, is the increase in volume per unit volume when a liquid is heated in an expansible vessel. Now, according to the question, the metal is said to be heated. And we're not told that the metal is expansible. We're not told that the metal contains any liquid. So for that reason, I'm taking the apparent expansivity to be equal to 0. That is why I told you, if I'm in examination hall, I'm going to approximate the fact that the real expansivity will be equal to the cubic expansivity, and that's going to be 6.3 times 10 to the power of 4 per Kelvin. So this is likely the interpretation I can give to this question. Otherwise, I will conclude that the question is not correct. Now, why did we say that the real expansivity is equal to the cubic expansivity given? Simple. For there to be apparent expansivity, the vessel that is being heated is expected to contain a liquid. Are you following, right? It's expected to contain what? A liquid. And that vessel will be expected to be expansible. But we're not told anything like that in this question. Therefore, I comfortably go with option A. All right, having explained this, we shall move on to the second question. Remember, you can copy this. You can also screenshot so that it will be faster for us to follow up. That's the solution to question number 1. So take a look before we move on to question 2. All right. So we're going to look at question number 2 provided by group 1. Question number 2 reads, a metal rod of length 100 centimeter is heated from 20 degrees centigrade to 80 degrees centigrade. A metal rod of length 100 cm is heated from 20 degrees centigrade to 80 degrees centigrade. If the coefficient of linear expansion is 1.2 times 10 to the power of minus 4 per Kelvin, if the coefficient of linear expansion is 1.2 times 10 to the power of minus 4 per Kelvin, what is the change in length of the rod? What is the change in length of the rod? Option A, 0.06 centimeter. Option A, 0.06 centimeter. Option B, 0.12 cm. 0.12 cm. Option C, 0.24 cm. 0.24 cm. Option D, 0.36 centimeter. 0.36 cm. So let us see how we solve this second question. Now we're given question number 2. Just write this solution in it. Let's define the data given to us so at least you can follow up. From the question, we're given the length of the metal rod. That's the initial length. Let me use L1 for it. And it is given as 100 centimeter. Now, on a normal, I am meant to convert this cm to meter, but I won't do that. There is no need for that because in the option, the change in length of the rod, the unit of the options provided are in centimeter. For that reason, there is no need of converting this guy. All right, we're given the temperature. Initial temperature, according to the question, is 20 degrees centigrade, and the metal was heated to a final temperature of 80 degrees centigrade. A final temperature of what? 80 degrees centigrade. Now, if the coefficient of linear expansion, that is linear expansivity, coefficient of linear expansion, simply linear expansivity, we use alpha for it. In the question, it was given as 1.2 times 10 to the power of minus 4 per Kelvin. So if the coefficient of linear expansion is given as this guy, we are required to find the change in the length of the rod. Change in the length of the rod. When you hear change in the length, this is what they ask you to find. And change in the length is simply equal to the final length L2 minus the initial length L1. So this is what we're asked to find. Aditya Chohen, can I ask a question, please? Differentiate between current and voltage. Why would you ask such question? Why would you ask such question now? I can't answer that question. What we are treating is thermal expansion. I have told you guys, if you have a special need, and I'm yet to see many of you request to join the GMAETS 41's WhatsApp group, so that if you have a personal need, you can send the question across requesting GMAETS 41 to assist you if it is to make a video on a particular topic. All right, when I am live like this, there are certain things I can't take. Reason is simple. I can't be teaching topic A and someone is asking question on topic B. I don't know if you expect me to leave topic A and start talking about topic C. This is not a question and answer segment, okay? Any question I will entertain, please take note, will be based on the topic I am treating. Thermal expansion. I found out that this stuff, the 80 cut off. Let me adjust the screen a bit, please. I mean the camera rather. Let me adjust it. I'm sorry about that. Okay. So I had to talk about this so that you don't feel offended that I am not responding to your question. Is that okay? Let's move on. Okay, so yeah. Onyebuchi, thank you for telling me to continue, and that's the right thing I should do. Now from here, we are going to recall the linear expansivity formula. The coefficient of linear expansion is equal to change in length divided by the original length times change in temperature, where the change in temperature is final temperature minus initial temperature. Now in chemistry, for example, under gas laws, you meet stuff like temperature. If it is given in degrees centigrade, it is expected that you add 273 to it in order to convert from degrees centigrade to Kelvin. Please don't punish yourself about that under this calculation, this topic. You can solve in degrees centigrade directly. You can solve in Kelvin directly. If you start converting each of these guys to Kelvin, you are wasting that time, because at the end of everything, you still get the same answer. Therefore, we shall go straight on and then write that it implies that our change in length, rather, you need to get it, you cross multiply. I want to make change in length subject to the formula first. But you can decide to substitute here directly. The choice is yours. That's going to be the linear coefficient of expansion times the initial length, then times temperature change. Substituting, our change in length will now be equal to alpha, linear expansion coefficient is this, and then times the original length, which is 100 centimeter, times change in temperature is 80 minus 20. If you work on this, what will you get as your change in length? Let us find out what you're going to get. I am assuming that I don't have calculator, because per se in JAM, I've always said that it's as good as you are restricted from using calculator, except they upgrade their systems calculator. Remember that the systems calculator does not have raised to power something, I guess. Still one area where I want to appeal to JAM and her official, right? Her official. So perhaps I'm going to speak to that fact with just a particular video dedicated to them, where I would have to appeal the idea of telling students not to use calculator. And I don't know, like I've said, When last calculator has become a malpractice stuff? I don't think that. Now that even the exam is CBT, in all those computer-based centers, they can track them to be careful of the calculator they use. You can decide a particular calculator that students can use. As I know of our normal scientific calculator, that's okay for them to use. So it can help to facilitate their calculations. Because that's stuff that, yeah, speaking to Jam now per se, in case any official gets to get in contact with this video. That systems calculator, the truth is, it rather wastes students' time. Yeah, it wastes candidate time. By the time they will drag mouse going to clicking on this number and that, we can save students this stress. Just a humble appeal anyway. I'm not taking jam, but as an educator, I think we know what's really obtainable. Otherwise, then tell WAEC to stop students from using calculator. I've seen a reason why students will be allowed to use calculator in that examination, and then in JAM they are denied that. It makes no logical sense. Besides, our schools don't teach students, a lot on how to work with a calculator. It's not part of the curriculum. 80 minus 20 will give you 60. 60 times 100 will give you 6,000. This 6,000 you are seeing from here is the same as 6 times 10 to the power of 3. I repeat that again. 80 minus 20 is 60. 60 times 100 is 6,000. If you're an examiner, the fastest thing to do is to convert that 6,000 to standard form, which I've shown you here. So that in multiplying, you will do 1.2 times 6. Those numbers that are not 10, multiply them. 1.2 times 6. 6 times 2 will give you 12. So you write 2 and carry 1. Then 6 times 1, put point, will give you 6. Plus the 1 you carried, you get 7. Then times 10, you've multiplied 6 by 1.2. So the next thing you have to do, pick one of the 10s and then add the power of the 10s using multiplication law of indices. That's going to give you minus 1. Minus 1. Because minus 4 plus 3 will give you minus 1. And at 7.2 times 10 to the power of minus 1 will still give you 7.2 divided by 10. And 7.2 divided by 10 is 7.2 divided by 10 is 0.72 centimeter. This is the change in length. This is the change in what? In length. All right, so that's how you calculate, or solve this particular question. That's how you solve it. Unfortunately, the answer is not here. Unfortunately, the answer is not here. We can look at it and see, once again, did we make any mistake? As a student, per se, when you solve a question, you want to ensure that you are very much accurate. The values given to us, the length of the meter is 100 centimeter. Look at it. And then it is either from 20 to 80 degrees centigrade. Then if the coefficient of linear expansion is 1.2 times 10 to the power of minus 4, yep. What is the change in length? So the formula from 20 to 80 is 60 degrees. 60 times this should give you 6,000. Converted to standard form. Of course, I think that's it. There is no error in this. No error. Even if I convert this to, let us say that I convert this to meter. If I convert this to meter, it's going to give me 1 meter, which means that this will be 1 meter. 60 times 1.2. 60 times 1.2 will give us what? So you multiply this 6 by this, you get 7. That should be 72, right? Can break this down to 6 times 10 times 1.2. And then this times this is 12 times this is 72. So we're very correct in our calculation. The options provided happen to be wrong somehow. Yeah. Option A is 0.06 centimeter. Option B is 0.12 centimeter. Option C is 0.24 centimeter. Option D is 0.36 centimeter. So the change in length given, this is what we got here. So I see no reason why that is equal to any of the options given. But all the same, I say group 1, you can see what you provided for us. But let the option not be our interest. Our interest should be what is being solved, right? How we approached it. I want to let you know this, please. Imagine you are asked to find the new length. The new length, that is L2. The new length, L2. The new length, L2, is going to be the change in length, which is 0.72 centimeter. And then L1 will be added to it, because to make L2 subject to a formula, L1 will meet this change in length, which means that the new length of this rod or metal, whatever it is, when it was heated, the new length would be 100 plus 0.72 centimeter. The new length, L2, is equal to change in length plus L1. Take note, we have calculated change in length, add it to L1, and then you get the new length. I have to say this because there are some questions that an examiner can give to you, and you are simply just asked to calculate maybe the new length, as the case might be. All right, we are done with this particular question 2. Let us move on to question number 3. If you have any question on what we've done, please remember you can always ask. So I thought the change in length should be L2 minus L1. Yes. You are very correct. Mary Cynthia, you already recorded 0.72 centimeters. Sweet. 0.72 centimeter. That's very correct. That's very correct. So Chibike Moses, I thought the change in length should be L2 minus L1. Yes, you are very correct in that. And that's what I did on the board. I used delta L to represent that change in length. Good. I am happy you get it now. So like I said, the correct option is not there as provided. Group 1 must tell us where you got all these your options from. Let us move on to our next question, number 3. Question 3. A rectangular sheet of metal. A rectangular sheet of metal has an area of 0.5 square meter. A rectangular sheet of metal has an area of 0.5 square meter at 20 degrees centigrade. When heated to 80 degrees centigrade, the area increases by, take note of that. I'll take it again. When heated to 80 degrees centigrade, the area increases by 0.01 square meter. Whenever you hear that statement, they tell you the value by which something either increases or decreases. Let me tell you a secret. It means they have given you the change in the value of that thing. If I say that your time of watching GMAETS 41's lesson has increased by 2 hours, it means your time factor, the original and the final, if you subtract it, you get 2 hours. All right, let us move on, please. What is the coefficient of area expansion? What is the coefficient of area expansion? A rectangular sheet of metal has an area of 0.5 square meter at 20 degrees centigrade. When heated to 80 degrees centigrade, the area increases by 0.01 square meter. What is the coefficient of area expansion? So from the information given to us, the initial area of the metal has been given to us. So can I say A1 is equal to 0.5 square meter? If you are sitting for JAM, for example, you don't need to declare this data. You don't need it. I've always said this. You read the question is appearing on screen. You know what each of those parameters represent. If you have the formula in your brain, immediately start substituting. So as you solve, are you following, right? Don't need to be declaring that A1 is equal to this and that. It's a waste of time. If you can define them on paper that A1 is this, theta 1 and theta 2 they are this, then why define it on paper in the first place? You can just, with the formula, start substituting directly. I'm doing this so that at least as much as all of you can follow. Now, theta 1 is 20 degrees centigrade. Then theta 2 is equal to 80 degrees centigrade. We are given the change in area was already given because we are told that the area increases by heating it from 20 degrees to 80 degrees. Initially, the area was this. Now to move from 20 to 80, the change in area, the additional value of area, the increase in area is that value given to us, which is 0.01 square meter. What is the coefficient of area expansion? Coefficient of area expansion, we use beta for it. We use beta for it. We don't know. So I want to find the coefficient of area expansion. And this is a 1 plus 1 calculation because the formula is still similar to that of coefficient of linear expansion. It's just for you to change all lengths to area. Now recall that this is equal to change in area per unit area, which is all over the original area, then times change in what? Temperature. That is what we have there. That's the formula. So we are looking for coefficient of area expansion. So our change in area is 0.01 divided by the original area 0.5 multiplied by temperature change is from 20 to 80, which is going to give you 60. Are you following, right? So no need of theta 2 minus theta 1. It's a waste of time. So the coefficient of area expansion becomes, let's find out, 0.5 times 60 is going to give you 30. So that this becomes 0.01 all over 30. 0.01 all over what? 30. And how can you divide 0.01 all over 30? How can you divide it? All right? So you might decide, we have 2 decimals in the numerator here, and we have no decimal in the denominator. So I can choose to multiply the top by 100, multiply under by 100, so it will now be 1 over 3,000. 1 over what? 3,000. Then you divide that 1 over 3,000. Do you understand that? We have 2 decimals here. So normally if you are dividing a decimal number by another, it's usually expected maybe you convert to a whole number. Since it's 2 decimal, multiply the top by 100, multiply under by 100. So that this will give you 1 over 3,000. And let me show you what you do about this in the exam to be fast. Like I said, I am not in support of the fact that students are being restricted from using calculator. I feel like during our time, they should define a calculator to use. If you don't want students to use powerful, machines as calculator, it's understandable. But you can define a certain calculator and then mandate all students to buy. Nothing is there. Nothing. And we used to know this scientific calculator that WAEC are providing, that standard that any student should be allowed to use in examination. I don't know if I'm communicating in any sense, although not to you student. I'm saying this so that you guys can also share this information. You can tag JAMB as well. So I hope I will make a special video to address JAMB chairman, right? I think Professor Ishak, or that should be the name, I can't really remember. But it's just an appeal, nothing is there. So that at least stuff like this can be easy for students. Why do I can solve these stuff most times without calculator? The truth is, not all of us as educators are coaching students in that direction. Not. Most schools these days, you go to them. In fact, one student step SS3, SS1, teachers even start mandating them to buy calculator. So I remember a child I trained in primary school many years there, between 2017 to 2020, thereabout, right? 2017 to 2019, something of that kind. This little boy, I trained him very well to be independent of calculator. He got admission to secondary school right there from JSS1. In fact, in their prospectus, how do they call that thing? In their secondary, they indicate, as in they told the student to buy calculator. So most of our, scholars have been built in that direction. Like I said, I don't see anything wrong anyway in the use of that calculator, even though for me, I don't usually advise students to be dependent on it. Now this 1 over 3,000, I can use reciprocal negative index flow rather of indices is the same as 3,000 raised to the power of minus 1. Then I'll now come to this 3,000. You know that 3,000 in standard form is 3 times 10 to the power of 3. So if 3,000 is 3 times 10 to the power of 3, you raise it to the power of minus 1. According to power law of indices in mathematics, this power 3 will multiply this power minus 1, I guess, right? It's going to multiply this. and then also multiply this 3. So that this thing you are saying is going to be 3 raised to the power minus 1 times 10 to the power of minus 3. Because this minus 1 will affect this 3, it will also affect this 10 raised to the power 3. Then 1 over 3 is 0. At least I know that. 1 over 3 is 0.3333, right? Let me just pick this to then times 10 to the power of minus 3. I can move this point once, because in standard form you should have a 1 non-zero digit before the decimal point. So this becomes 3.3 times 10 to the power. You move the point once to the right. Therefore, you subtract 1 from this minus 3. You now get minus 4 per Kelvin. So this is the value of that guy. That's the value of coefficient of area expansion. All right, we are done with this question, and I can't remember dictating the options to these guys. Therefore, I am going to dictate the options. Now, option A, 1.0 times 10 to the power of minus 4 per Kelvin. Option B, 2.0 times 10 to the power of minus 4 per Kelvin. Option C, 3.0 times 10 to the power of minus 4 per Kelvin. Option D, 4.0 times 10 to the power of minus 4 per Kelvin. The correct option is option, this is what we got, 3.3. Since all of them is 0.0, you know, if you are rounding off this 3 will be rounded down. So this is the same as 3.0 times 10 to the power of minus 4 per Kelvin. And that goes with option C. It goes with option C. So look at what I did here. I don't know. I just pray and hope that our professional exam bodies do the needful and stop imposing unnecessary burden. Yeah, it's unnecessary. There is no logical reason, like I said, of why students should be denied using certain calculators in exam. For me, that systems calculator is a time-wasting stuff, right? That's what I feel. Now, we are moving on to question number 4. So I could say or this. And that goes with option C, like I said. But let's indicate option C. That's the correct answer. Question number 4. All right. A steel plug has a diameter of 5 centimeters. A steel plug has a diameter of 5 centimeters at 30 degrees centigrade. At what temperature will it fit exactly? At what temperature will it fit exactly into a hole of constant diameter? At what temperature will it fit exactly into a hole of constant diameter 4.997 centimeter? In brackets, coefficient of linear expansion of steel. Coefficient of linear expansion of steel is 11 times 10 to the power of minus 6. 11 times 10 to the power of minus 6 per degree centigrade. That's 11 times 10 to the power of minus 6. I don't know. I don't understand group 1. I'm actually expecting, okay, maybe based on personal experience and how these coefficients of whatever are given in standard form. That's supposed to be 1.1 times 10 to the power of minus 6. 1.1 times 10 to the power of minus 6. That's what I'm thinking of. But who am I to just change the question provided? I'm going to solve with that 11 times 10 raised to the power minus 6. Now the options provided: A, 27.3 degrees centigrade, B, minus 24.5 degrees centigrade, C, 2.7 degrees centigrade, D, 24.5 degrees centigrade. Why I cannot change these values you gave? Of course, it's because if you're in the examination hall, you can't go changing questions that the examiner provides. All right, so in as much as, at least from a personal experience, I feel like this is what the value should be, I can't change it. I'm going to solve with respect to the 11 times 10 to the power of minus 6 per degree Celsius given here. So a steel plug has a diameter of 5 centimeters at 30 degrees centigrade. At what temperature will it fit exactly into a hole of constant diameter 4.997 centimeters? Coefficient of linear expansion of steel was given to us. So look at the parameters given. The diameter of that steel rod, a steel plug has a diameter of 5 centimeters. So diameter is equal to 5 centimeters at 30 degrees centigrade. From this diameter, we are going to get the radius, possibly, because looking at this, at what temperature will it fit exactly into a hole of constant diameter? So it is assumed that this steel plug is circular. That is why, of course, we're given the diameter. Even if we think that a steel rod is something like this, remember, if you have something like this, we can approximate this side that has length like this side. We can approximate this side to be diameter. Because if I choose to do something circular like this line will be the diameter of the line of this shape or rod. Now, it is as if this guy is to be fitted into a hole. Is to be slotted into what? A hole. Like when you are trying to maybe plug something into a socket. Now, the diameter of the socket was given to us because the question asked, at what temperature will it fit exactly into a hole of constant diameter 4.997? Now, the diameter of this guy, let me try to give you a sketch of, the diameter of this guy is 5 cm. Now, this is to be plugged into a hole, to be fitted into a hole of constant diameter 4.997. So let us assume that this is the hole. This is the hole. And then the diameter of this hole, is what? 4.997 centimeter. 4.997 centimeter. So if you look at this, you would see clear that the diameter of this steel plug is greater than the diameter of this guy. So definitely for this to be fitted into this hole, there should be a little compression here. But of course, if you look at this value, it is approximately equal to this. That 4.99 something is approximately equal to that 5. But the idea is simple, right? We are going to use this as L1 and L2. So this is L1. We're going to take the hole that is going to be fitted into to be L2. Because of course, if this rod is coming, usually there are sometimes you try to force something to enter a tiny space. You try to meander your way, and before you know, the thing might just fit in. Okay? Because these two guys, they are almost approximately the same. Okay, so with this, we are given the temperature at this point, theta 1 is equal to 30 degrees centigrade. L1 is equal to 5 centimeters. So here, theta 2, we don't know. At what temperature, final temperature, will this guy fit into this? Now, the coefficient of linear expansion, alpha, was given to us. Alpha is equal to 11 times 10 to the power of minus 6 per degree Celsius. Don't forget, please, diameter is still the same as length. If I have a circle, a diameter is a straight line drawn passing through the center of that circle. You can extract that line as a straight line. So once again, recall that alpha is equal to delta L over L1 and then multiply by delta theta. Now coming here, we know the value of alpha 11 times 10 to the power of minus 6, even though I am thinking it should be 1.1 anyway. Now change in length is going to be 4.997 minus 5. Then we divide this by the initial length of that guy, which is 1. For this guy, this diameter to fit in here, something would happen. It's either this steel plug compresses, are you following? That it compresses to fit in, or it will cause an expansion here. It will cause an expansion here. As this guy is entering here, it's going to expand this guy. So this is the final length. This is the initial length. Now we divide it by L1. L1 I said is 5, right? 5. Then multiply by temperature change. The temperature change is theta 2, which we don't know, minus theta 1 is 30. So solving for this minus this will give us a negative result. It's going to give us what? A negative result. So we can do the subtraction. 4.997 minus 5 is the same as 5.000 minus 4.997. If you do the subtraction like this, anything you get, you fix your what? Your minus. Borrow 1 from this, you know those things. This is going to be 3. This is 9. So 9 minus this is 0. This is 9 also 0. And then 0. So the change in length is 0.003 centimeter. All right. So this is equal to negative 0.00. Let me write it below. Negative 0.003. Negative 0.003. Then divided by this 5 can actually multiply this guy to give you 55. 55. Taking this 5 to multiply this, then will now be left with theta 2 minus 30. If you cross multiply, your theta 2 minus 30 is going to be equal to minus 0.003 divided by 55 times 10 to the power of minus 6. We can convert this to standard form. This is negative 3 times 10 to the power of minus 3, then divided by, I hope this has not cut off from the screen. Let me be sure. Let me check over here. Okay, still showing. So divided by this, I'll write it as 55 times 10 to the power of minus 6. We'll take care of this 10 to the power something, 10 to the power something. Let's divide this 3 by 55 first. Minus 30, theta 2 minus 30 is equal to 3 over 55. What are we going to get? That should be there about 0. 55 can go into 3 0 times. You'll be left with 3 as a remainder. Okay, so 0.3. That 3, you attach 0 to the back, you get 30. Divide 30 by 55, you still get 0 remainder 30 because, 55 is bigger than 30. So 55 can go into 30, still 0 times. That 30 will be remaining. So what do you do with that 30 that is remaining? Attach 0 to the back. If you attach 0 to the back, you get 300. Then divide by 55. So how many times can 55 go into 300? If you say it is 6 times, 6 times is greater than this already. I can try 5 times. If I say 5 times 5 is going to give you 25, right? 5 carry 2, 25 and then 27. That's going to be 275. So 5 times can go because 6 times will be greater than this 300 already. 6 times is going to be 0, carry 3, the 330. So 55 can go into 300 5 times. 5 times. Now, how do you get the remainder? It's going to be the 300 minus 275. And 300 minus 275 will give you 25. That 25, attach 0 to it to get 250. Divide by what? 55. 55 can go into 250. How many times? I presume 4 times. 4 times 5 will give you 20. Right, 0 carry 2. 4 times 5, another 20. Plus the 2 you carry, that is 220. Yeah, 4 times. If you move 5 times, it will be greater than 250. Okay, so this is 4 times. I'm done dividing this. You can use your calculator. This is minus. You can use your calculator if you so wish. Doing this thing, looking at real exam situation. Now, how do we handle this 10? Minus 6 will go up to become plus 6. Then minus 3 plus 6 will give you 3. Will give you 3. So this is theta 2 minus 30 to be equal to 0.054 times 10 raised to power 3 is the same as 0.054 times 1000. And that simply means you are moving a point 3 times. 1, 2, and 3. So this times this will give us minus 54. minus what? 54. Now collect like term. Therefore, theta 2 will be equal to, this 30 will go over there, and then you have 30 minus 54. 30 minus 54 is the same as 54 minus 30, which is 24. So this is negative 24 degrees centigrade. The final temperature is going to be negative 24 degrees what? Centigrade. Negative 24 degree centigrade. That's going to be the final temperature of this guy. All right, we are done solving this. We are done solving this. And in the option, we have negative 24.5 degrees, and we have 24.5 degrees. Negative 24 and 24.5 degrees, right? So from here, we see the guy is going to carry negative. I'm sorry, that 0.5 you got, if I had continued to do this division, remember when I did 250 divided by 55, we said it's 4 times, and I didn't proceed again. That 4 times, if I do, I divided 250, right, by 55, and I said it's going to be 4 times. To get the remainder, is meant to be 250 minus 4 times this would give us, I think we checked, it was 220. That 220, subtract it from what you divided 250. 220 minus 250 is going to give us 30. It's going to give you 30. So 30 could have been the remainder here, which you are now meant to attach 0 to the back of the 30. You get 300. Divide that 300 by 55 again, which will be 5 times. So permit me, please. This is meant to be another 5 here. So that by the time you move your point and you come here, this will be minus 54.5. So that this thing will now be 54.5, which if you subtract, you get minus 24.5 degrees centigrade. See, all these things are stuff about calculating, your mental maths. Your mental maths. And the truth is, if you are very good with your multiplication, I've always been singing this thing in my video lessons. If you are very, very good with your multiplication, you can be very fast in this in your examination hall. Remember why I'm doing all these things? Because of the fact that you're not allowed to use a calculator you can press. And that system's calculator to an extent to waste your time in clicking all these digits, raised to power something. You don't even have raised to power stuff in that calculator. I can't remember you having something like that. So you see, this thing is telling you that the final temperature, because according to the question, we were asked, at what temperature will it fit exactly into a hole of constant diameter? So if the temperature of that steel plug initially was 30 degrees centigrade, the final temperature of that steel rod will now become minus 24.5 degrees centigrade. There is the temperature reduced from 30 to minus this. And when something is reducing, it's contracting. The diameter will be doing what? Contracting. There are 2 options that could likely confuse the students here. Listen to the options once again. Option A is 27.3 degrees centigrade. That one is completely off. Option B is minus 24.5 degrees centigrade, a suspect. Option C is 2.7 degrees centigrade, completely off. Option D is 24.5 degrees centigrade. So the difference between option B and D is minus. Both of them is 24.5 degrees centigrade. But option B, as in boy, option B has minus. Option D, as in dog, right? Or delay, D, does not have this minus. So a student might be confused, and you may get into trouble because of the placement of this numerator. Remember, I told you this is the final length, because you had the original length of this guy, trying to fit it into something. So you need to do something to the temperature of this steel plug. Since the diameter of the hole is smaller than the diameter of the steel plug, that steel plug, the temperature has to be reduced so that the steel plug will contract in order to be able to fit in into this hole. Do you get that right? And that is why the final result is actually minus, following the arrangement of this change in length here. Are you following? Final length minus original length. If you had placed this as 5 minus 4.997, you would have gotten into trouble, because you would get positive 24, option D, 24.5. And you're getting that 24.5, it's going to be something. All right, we are moving on, please. This will take us to question number 5. This will take us to question number 5. I hope this did not cut off from Yep. Is there? Teacher, please talk slower. Code Bro, I love you too. Thank you for joining. Let's see if you react. I hope that does not refer to me. All right, clip craze, right? I'll try to talk a bit slower, but I'm not fast either anyway. Let's move on to our next question. That's question number 5. Q5. Question 5 reads, two metals, P and Q. Two metals, P and Q, are heated through the same temperature difference. Two metals, P and Q, are heated through the same temperature difference. If the ratio of the linear expansivity of P and Q, if the ratio of the linear expansivities of P and Q is 2:3, the linear expansivity of P, the linear expansivity of Q, their ratio, this ratio Q is equal to 2:3. If the ratio of the linear expansivities of P to Q is 2:3, and the ratio of their length, is 3:4, the ratio of their length, so that is a length of P to length of Q, is equal to 3:4 respectively. The ratio of the increase in lengths, of P to Q, the ratio of the increase in length of P to Q is, the ratio of the increase in length of P to Q will be what? So look at increase in length. You know, we use delta L for it. Delta L, that is increase in length. So we are asked, what is going to be the ratio of the increase in length of P to Q? So we're going to write it delta L of P ratio delta L of Q, we do not know. Option A, 1:2. Option A, 1:2. Option B, 2:1. Option C, 8:9. Option D, 9:8. How do we solve this question? Please let me plug this device a moment as I analyze this question. All right. So this is the information given to us. We have two materials. Their linear expansivity of P to Q was given to us in ratio form. The length of those guys, the ratio was given to us. We are asked to find the ratio of the change in their length. That is the ratio of increase in length. You see this length given to us, LP and then LQ. That is their original length. So you're going to permit me to use L1P and then, LP1. That is initial length of material P, and then LQ1, initial length of material Q. Yes, that is the initial length. It's not their new length. It's not their final length. It is the initial length given to us. The final length or new length was not given. And of course, we don't need it. Because what the examiner asked us to find is the ratio of the increase in length. Increase in length is final length minus initial length. That is L2 minus L1. L1 was given to us. We don't need L2. It's not necessary. Now, what do you do in solving this question? It's a simple one, but you know, when someone sees this, we might kind of be thrown off. But relax. I always tell students, use the knowledge of the known to deal with the unknown. Now, this question is based on linear expansivity because we are given the linear coefficient of expansion of the two materials. So all I have to do is to quickly remember the formula of linear expansivity. Write it for those two guys and then take the ratio. From the ratio, I'll definitely get the ratio of these two guys given to us, the ratio of the increase in length, and then you just simplify. So from here, I'm going to recall that we know that linear expansion, that is coefficient of linear expansivity, is equal to change in length all over the original length. Like I say, permit me to use subscript 1 for these guys. Then delta theta. Now, if you look at the question, we are told that they were both heated through the same temperature rise. They were both heated through the same what? Temperature rise. That was how the question presented it. Are you following? Material P and Q, both of them were heated through the same temperature rise, which means that delta theta for both of them will be the same. And if delta theta for both of them is the same, if you take the ratio, it's going to be 1 to 1. And that 1 to 1, you know, it's just as good as they cancel out. Because if one multiplies anything, it will give you that anything. Now, let us write this formula for P and write it for Q. Coefficient of linear expansion for P is going to be delta L of P divided by LP1, then delta theta. Then that of Q is going to be equal to delta LQ divided by LQ1 times delta theta. You notice that I did not bother myself writing delta theta P and delta theta Q. It's of no use. We don't need it because both of them, they have the same temperature rise according to the question. They were heated through the same temperature. Now, we are dealing with ratio here. You can see that the ratio of the coefficient of linear expansion for both materials were given to us. So quickly take the ratio of these two guys. And ratio is simply division, you know. The ratio is going to be the linear coefficient of expansion of P divided by linear coefficient of expansion of Q. Will now be the increase in length of P. You write this guy. Look at this formula for linear coefficient of expansion of P, which is all these terms, LP1, then delta theta. Divide this whole thing by the formula of linear expansion, linear coefficient of expansion, or simply linear expansivity of that of Q, which is written as delta LQ divided by LQ1, then times delta theta. So this is what we've got. That's the ratio. That is the what? Ratio. So all we have to do now is to simplify. You know, mathematically, this term you are seeing here can be written as this over this equal to, I'm just trying to waste our time here. I'm sorry about it so that every one of you can follow through, right? If I go to say cancel this, and then I inverse, somehow, somewhere, some persons might just be confused. Remember, GMAETS 41's platform is a real platform of learning. That's the main thing that this platform is established for. So I try as much as I can to carry as many as possible along. You see this division sign? You know, if you are dividing fraction, you know what to do. Change it to multiplication and then inverse this guy. If I inverse, I'm going to get LQ1 times delta theta divided by changing, that is the increase in length in Q. Now, mathematically, this is going to cancel this, you know that, right? Then you now have increase in length of material P over increase in length of material Q. You also have this guy, which is the original length or the initial length of Q over the initial length of what? P. At this point, we can now fix our values. Linear expansivity of P is 2. So it's going to be 2 all over. That of Q is 3. That's going to be equal to increase in length of P. We don't know it. Increase in length of P, so you maintain it. delta LP. Remember, that is divided by, I can shift this one under this multiplication. So it does not matter how you decide to arrange the numerators and the denominators. I want to arrange the increase in length together and then the initial length together. So this increase in length of Q will now come over here, then times the initial length of Q all over the initial length of P, which I can substitute for. I can substitute because their ratio was given to us. LQ1, the ratio, LQ1 is 4. So I'm going to write 4 all over LP1, the initial length of P, is this first ratio, which is 3. So with this, all we have to do is to make this guy subject of the what? Formula. I know to do that, just follow along. Let me do it once. Are you following, right? Let me do it once. This is just like cross multiplication. This 4 will multiply this 3. And then this 3 will multiply this 2. Cross multiplication. To make, therefore, the increase in length of P divided by increase in length of Q. You know, this thing is ratio. And that's the format in which we have to get it. The ratio of the increase in length of P to the increase in length of Q is what? We don't know. Look at it, this over this will now be equal to, mathematically, this 3 will multiply this 2 to give you 6. This 4 will multiply this 3 to give you 12. And if you solve this, you are going to get 1 over 2, which means that the ratio is 1:2. 1:2 is the value of this guy. The ratio of the increase in length of P to the increase in length of Q is 1:2. If it is increase in length of Q, so the increase in length of P that we asked to find, it will be 2:1. So this is how you solve this particular question. Now, guys, we have one of the options that is 1:2. I guess option A also. I can't remember. I'm going to check right away and then dictate the options again. But I can go through how we analyze this particular question. Let me adjust this. Seems like. Thank you very much. ZI8IX. I mean ZL8IX. I appreciate your commendation, telling me that this is amazing. Shanti Pereira, bro, I can't understand, bro. So what is it that you cannot understand? If you can't understand, you can ask a specific question. Ask what? A specific question where you don't understand. You can ask and then I can give explanation to that. But remember that this has a topic. And before you talk about some of all these formulas, you know, linear expansivity, area expansivity, volume expansivity, when you are being taught, you should know the formulas to those guys. I want to use this opportunity to advise all of you, please, and urge you all. It's not just all about the live class, the live class, the live class. This platform, right, GMAETS 41's channel, has video lessons on various topics where I took my time to teach step by step a particular topic, you know, laws in the topic, if the topic contains laws, theory, if the topic contains certain stated theory, then formulas, right? So you can actually follow up. Make sure you visit the channel. How can you go to my channel directly? Under any of my video, you have the GMAETS 41's blue logo. Click on that blue logo. It will take you straight to my channel, to the GMAETS 41's YouTube channel. Then you can check on the playlist. Click on the playlist. I tell you what you're going to see there. You'll see academic wonders. Yes, on different subjects, courses. So you can take the ones that you want to take. So by the time you have classes like this, you can follow through. Are you following, right? Meanwhile, Shanti Pereira, right? I don't know if I got the name correctly. If there's anything you don't understand, do me a favor. Just ask a specific question. All right. How did you get this particular? You can type it quickly. How did you get this part? Or just mention, I don't understand this part. And I would try to respond to you. Meanwhile, like I said, please, please and please, do yourself good. You see, I try to understand students a lot because I had been a student before. I know that what students go through is not easy. I must confess to that. It's not just all about Nigerian alone. Although we look at our own as only God knows, because it seems like nobody cares about the students and whatever, right? Or in other parts of the world also, they have their own peculiar challenge as well too. We can help ourselves, you know. Technology has made life quite easy. I can connect from anywhere in the world to any particular, you know, class. So if you enjoy my lessons, if you love what the GMAETS 41 is doing, what stops you of joining our WhatsApp group? Where, like I said, if you have a need, okay, so I want you to do something on this topic, you will indicate it. Then I'll create our time and do something for it. However, you can prioritize your request by becoming a channel member. Very important. You have to support this channel. It's not easy for me. I've said this before. Don't worry, I will share my experience with you guys on the 4th of April, because of course, I'm going to talk about my 1 year of fighting. Yeah, fighting to survive health-wise. But as long as there is life, and our God and helper Jehovah has always continued to support the GMAETS 41, like I said, all glory and honor and praise go to him for all of his goodness. So you too can support this channel. Doesn't take much. For example, as this class is ongoing, in the comments section, just by the right side, you have currency icon. If you tap on it, you can support this channel, whatever you have. You can send GMAETS 41 a super thanks. You click on it, YouTube have, you know, various convenient packages with which you can use to support a creator. Support me. Yes, I need it. In as much as I will never like come up and be talking about it, make his video, and the truth is every creator needs your support. So you can send a super chat, you can send a super thanks. You can also become a channel member. If you're becoming a channel member, consider selecting from platinum level. If you go to a platinum level, you have wonderful video lessons from there. The higher you select, the more benefit you get from this channel. And you can become member of our learning community. In the channel membership, there you support this channel on monthly basis. Monthly basis. Super chat, super thanks is a one-time support. So please, but very much important, see this number, you can send a message to it on WhatsApp, right? Request that you want to be added to the GMAETS 41's WhatsApp group. So there you get updates about our classes. All right, let us move on, please. We still have other questions, right? I'm a math student. Is this physics? Yes, this is physics. And then remember that maths is also physics. Maths is also what? Physics. We move on to question number 6. Question number 6 is not, okay, it's calculation. It's calculation also. I'm going to wipe this part. See how this channel continues to encourage you guys on the need to be independent of calculators. There are a lot of things I could have just, you know, press calculator and tell this is the answer. But I try to encourage you the importance of your being independent of calculators. You can do that. You can do that, right? One day I will share one funny experience I had when I decided to teach at the final level I taught in conventional schools, right? In primary school level between 2017 to 2020. I'll tell you the experience I had. I was handling exam class at the time, grade 5 and 6. So you see that an individual can decide to improve himself any day, anytime. You can do this, and I've always been singing the secret to improving your calculation skills. Multiplication table is the key. Learn your multiplication at heart. Question number 7 reads, a glass bottle of initial volume. A glass bottle of initial volume, 2 times 10 to the power of 4. 2 times 10 to the power of 4 cubic centimeter is heated from 20 degrees centigrade to 50 degrees centigrade. Is heated from 20 degrees centigrade to 50 degrees centigrade. If the linear expansivity of the glass, take note, if the linear expansivity of the glass is 9 times 10 to the power of minus 6, is 9 times 10 to the power of minus 6 per Kelvin. The volume of the bottle at 50 degrees centigrade is, the volume of the bottle at 50 degrees centigrade is, I'm going to take the question again. I'll be faster and ready this time around. A glass bottle of initial volume 2 times 10 to the power of 4 centimeter cube. So the initial volume of the glass bottle, question 6, V1 is equal to 2 times 10 to the power of 4 cubic centimeter, is heated from 20 degrees centigrade to 50 degrees centigrade. So theta 1 is 20 degrees centigrade or Celsius. Theta 2 is equal to 50 degrees centigrade or Celsius. If the linear expansivity of the glass is, we are given the linear coefficient of expansion, not the cubic coefficient of expansion, not the cubic expansivity. What the examiner gave to us is the linear expansivity. Sadly, this question is based on volume or cubic expansivity. But don't worry, we are going to deal with it. It's 1 plus 1. Now the linear expansivity, coefficient of linear expansion, is equal to 9 times 10 to the power of minus 6 per Kelvin. We are now asked to find the volume of the bottle at 50 degrees centigrade is what? The volume of the bottle at this temperature. So in this case, the examiner is actually asking you to find the new volume, V2. You don't know. It is not change in volume that they want you to find. It is not increase in volume that they want you to find, just like some that we have treated. Increase is also quantity. Here it is increase. Here it is the new volume that they want you to get. Let's assume that this is the bottle and this is the initial volume. You now hit it. And let us assume now that the volume now increased to this point. So the value at this point, the new volume here, is what they want you to get, not the increase. So V2 is what we are calculating for. Now, this problem given to us is about volume. And whenever you are dealing with volume expansion, we talk about volume expansivity, which from the beginning of the class, I've already given a summary. Increase in volume per unit volume per degree rise in temperature. Solution to this, we want to recall. For volume problem, we should be talking about cubic expansivity, also known as volume expansivity. And the formula is final volume minus initial volume divided by initial volume times change in temperature. This is the formula. So you don't look at, we are looking for this guy. We don't know V2, the new volume. The volume at the final temperature, we don't know. That's our problem. But unfortunately, look at this. For us to calculate this V2, we are supposed to know this guy, volume expansivity. We're supposed to know it. Sadly, we still don't know this guy. We don't know the volume expansivity. But relax, like I said, it's 1 plus 1. Your examiner has given you linear expansivity, linear coefficient of expansion. So with this linear coefficient of expansion, you can calculate the volume expansivity using the fact that volume expansivity is equal to 3 times linear expansivity. And lest I forget, let me also tell you that area expansivity, that one of beta, is equal to 2 times linear expansivity, 2 times alpha. So these are relationships, right? You want to take note of. Volume expansivity is 3 times alpha, 3 times linear expansivity. And then area expansivity is equal to 2 times linear expansivity. In the thumbnail of this particular live class, you have something, displayed on that thumbnail, showing you that relationship. So with this, it means that our cubic expansivity is 3 times 9 times 10 to the power of minus 6 per Kelvin, which of course is going to give us 27 times 10 to the power of minus 6 per Kelvin. But I don't want to multiply here. Let's just leave it like that and then substitute here. Implication. In place of this cubic expansivity, I'm going to fix 3 times 9 times 10 to the negative 6 power. Then V2 minus V1 is 2 times 10 to the power of 4. 2 times 10 to the power of 4. Do we need to convert the volume here? Let's check the unit and see. The units of the volume given to us are in cubic centimeters, so no need of converting anything. Please pay attention to the units. Option A, 20,016.2 cm cube. 20,016.2 cm cube. That is 20016.2 cubic cm. Option B is 20,005.4 cm cube. That is 20000005. Then 0.4. Option C is 20,008.1 cubic centimeter. 20008.1 to 0008.1 cubic centimeter. Then option D, 20,013.5 cubic centimeter. That is 20013.5 cubic centimeter. So we don't need to convert this, since the options given to us, the unit of that final volume supposedly is in centimeter cube. So we shall divide this by 2 times 10 to the power of 4, which is the initial volume, multiplied by temperature change. What is our temperature change? Final temperature θ2 minus initial temperature θ1. θ2 is 50, θ1 is 20. Right? So 50 minus 20 is going to give you 30. Let's fix 30 in no time. So V2 minus 2 times 10 to the power of 4, you cross multiply. If you are cross multiplying, this is going to be 3 times 9 times 2 times 30. How about I decide to write this thing in standard form? This is the same as 3 times 10 to the power of 1. 3 times 10 to the power of what? 1. So that I'll now multiply 2 by 3, I'll get 6. Use the 6 to multiply 9. At least I know that from multiplication table that 6 times 9 is 54. Then multiply that 54 by 3. If you multiply 54 by 3, you should get 162. Yeah. 54 times what? 3. Like I said, if you know your multiplication table, at least from 2 to 9 times. If you're not giving 2-digit multiplication or 3-digit multiplication, you can arrange it in place values. So 2 times 3 from here is 6, times 9 is 54. 54 times 3, 3 times 2 is 12, right? To carry 1. 3 times 5 is 15 plus the 1, 16. So you get 162 times. In fact, that's what I'm going to do. If you like, multiply 2 times 30. You still get the same thing I'm going to get. 2 times 30 is 60. 60 times 9 is 540. Then 540 times 3. You multiply that 54 by 3 first, you get 162. And then attach 0 at the back, which is going to be 1,620. Then multiply by 10 raised to the power, whatever you have there, simplify your works. But like I said, I am going to work with 162 times 10. Remember, this 162 I got was when I broke down this 30 to what? To 3 times 10 to the power of 1. That guy is the same as what? 30. So that 2 times this, 2 times 3, or 3 times 2 is 6, times 9 is 54, times 3 is 162. Now pick all these terms and apply indices law. This is 10 raised to the power minus 6 times 10 to the power of 4 times 10 to the power of what? 1. Add all their powers by picking one of the base. Minus 6 plus 4 will give you minus 2. Minus 2 plus 1 will give you minus 1. Minus 2 plus 1 will give you what? Minus 1. Collecting like 10, V2 is equal to 162 times 10 to the power of minus 1. This will go there, you add, plus 2 times 10 to the power of 4. Then simplify. We have gotten to another point where you are adding numbers in standard form. When you are adding numbers in standard what? Form. Before you can add this and this, their powers must be the same. That's the power of 10. Must be the same. It is either you make this power 4 to become power minus 1, or you make this power minus 1 to become power 4. The choice is yours. However, in the option given, these guys were not written in standard form. So it doesn't matter, we can change any one of them to the other and then add up. Now look at what I want to do. I want to make this in power minus 1. And if I'm to make this power minus 1, it means I'll move my points to the right. How can you convert 4 to minus 1? To convert 4 to minus 1, you will subtract 5 from that 4. 4 minus 1 will give you, 4 minus 5. 4 minus 5 will give you minus 1. So if I want this 10 raised power 4 to become 10 raised power minus 1, I have to subtract 5 from this power. The question is, will I just wake up and then subtract 5 like that? No. There's a mathematical procedure you must follow. You have to move point 5 times. Now this 10 given to us, 2 times 10 to the power of 4. This 10, there is a decimal point just after that 2. This 2 you are seeing, there's a decimal point. So if I give you 2, move that point 5 times. 1, 2, 3, 4, and 5. So the point comes here. This will now become 2. At this point, you fix 0. Here is 0. Here is 0. Here is 0. Here is 0. Then the point. So you have 2, 0, 0, 0. 1, 2, 3, 4. 4 zeros. Then the point. This thing I did here has converted this power to minus 1. So this will become 162 times 10 to the power of minus 1 plus. You come over to this, and then this becomes 2, 0, 0, 0, 0. Yeah. Then times 10 to the power of minus 1. You have done the conversion. If you don't like this thing I am doing, this conversion, listen, you can just multiply this 2 by 10. This is 20,000. 20,000. Then look at this. This is 160 divided by 10, which is 16.2. Then you can now add 16.2 to 20,000. 20,000, and then you have 16.2. I guess that seems to be faster per se. This is something like this. 61 then 002. 20,016.2. But let's go this way at least so you can learn how to actually handle things in standard form. Like I said, if you don't like that, you can just convert them straight to whole number. Are you following, right? Decimal numbers rather. Decimal number, and then get your results in scientific form. All right, let us go. This is going to be, at this point, I can now add 162 to 20,000. If you add 162 to this, 2 plus 0 is 2. 6 plus 0 is 6. 1 plus 0 is 1. Then 20 here, which means this is 20,162. 20,162, right? This guy is 2 times 10,000. Yeah. We're in line. Let's see. So our V2 will now be add this and this. Like I said, 20,000. And they have 162. This is 2, 6, 1, 0, and 2. So why is this different? 20,000. Okay. Let's see the end. No problem. So I've added this to this. I'm going to multiply by 10 to the power of minus 1, which is the same as V2 equal to divide this by 10. If you divide this by 10, you're going to get 20,160. Then 0.2 cubic centimeter. Something seems to be wrong here. Something seems to be wrong. If you move this guy to this point, to the right, you have 2 times 10 to the power of 4. 2 times 10 to the power of 4. Then I move this point how many times? 5 times, I said. That 5 times will give you 2 point, then 1, 2, 3, 4, and 5. So this is 2. All right, the point was here before. Move to this place, have 2.0. So this is 0. This is 0. This is 0. This is 0. And this is 20,000. Now 20,000, you are adding 160 times 10 raised power minus 1 is same as 16.2. So if I add 16.2 here and I add 162 here, I'm supposed to get the same thing. Am I adding 162 to this? I should get the same thing. So I don't know why I'm getting different results with this conversion in standard form. Okay. 20,000. I have this 162.2. So why is it this 20,016? And then this is giving us 20,162. I don't know why it's that way. I don't know why it is that way. We're supposed to get the same result if I choose to solve straight on and I choose to convert. So let me take a look. Point from here, 1, 2, 3, 4. Okay, so I made a mistake. The number of zeros there. The number of zeros. I moved the point from here actually 1, 2, 3, 4. There's supposed to be 5 times. 1, 2, 3, 4, 5. This place is supposed to be a point. So that where you move that point from first, 0 has to come there. So that is it. I think I've gotten where I made a mistake here. So this is going to give us 200,162. 200,162. Good. So whether you solve by this method I'm using, converting to standard form, or you decide to divide this by 10, which is the interpretation of this, and then multiply this by 10,000, which gives you 20,000, you add up, the choice is yours. So from what I did, this is meant to be yeah, 200,000, because you move the point 5 times, times 10 to the power of minus 1. If I divide this by 10, I'll still maintain my 20,000. This is correct. So from here, this is meant to be, add this to this. If you add 2 plus 0, we give you 2. 6 plus this, we give you 6. 1 plus this, we give you 1. So this is 200,162 times 10 to the power of minus 1. I'm sorry that I had to do all this. There is a reason. I want to see how I can guide you also in standard form. Very important, because I think you need that a lot in your physics calculation when you meet all this standard form stuff. And it's one of the things that can help you to be able to survive some of all these calculations without a proper calculator. Now from here, multiplying this by 10 raised power minus 1 is the same as dividing this by 10. And if you divide this by 10, you're going to get 200,16.2 cubic centimeter. So this is the final volume, the new volume. That's the final volume. That is the new volume. I read the options for you already, and so you can actually say that the answer is there. But let me still dictate the options once again. Let me dictate the options once again. So we have question number 6. We are left with 4 questions actually. Question 6, option A, 20,016.2 centimeter cube. That is 200,16.2 cm cube. I don't think I need to punish myself reading others, because that's what we got here. 200,16.2 cm cube, and that's the answer. We have option B, C, D. Those ones are wrong. At the end of this lesson, when a copy of this video is made available, you can still listen to it again. You can retake and listen to the other values. All right, guys, we are moving on to question number 7, and this is interesting. I hope you are learning. I hope you are learning. Remember, you can send a message to this WhatsApp, to this number, and then on WhatsApp, request to be added to our general group. We're going to move on to our 7th question, and I hope nothing cuts off from that part of the board. Okay, that's good. All right. Question 7. I don't know. Someone is posting something in a language that I don't understand. So I don't know what we're going to do about it. Gigabits. I do not understand the language you are typing. What we are dealing with is thermal expansion. All right, it's thermal expansion. It is not elasticity. It is thermal expansion. Yeah. Gigabit, good. You already indicated 200,000 times 10 raised by minus 1, and you are very correct. Good enough. That is what I finally found out here, when I was moving the point. I made a mistake. 1, 2, 3, 4, 5. So from this point that the point moved, a 0 should be there. Another 0 here, making it 2, 3, 4, and 5. Then point will follow. All right, that's good. Thank you for following up. Question number 7. Question number 7 is not calculation, so just pay attention. I'll dictate it, and then we'll go for the answer. Thermal expansion of solids is an advantage in... Thermal expansion of solids is an advantage in... So when solids expand, where can you make use of it? Where can you consider it to be an advantage? So here we have effect of thermal expansion. Thermal expansion can cause sagging of telephone lines. That one is a disadvantage. It can cause expansion and contraction of railway track. It's a disadvantage. It can cause expansion of steel, metals, and buildings. It's a disadvantage because that can lead to a building collapse. Right? Now we have this one we call bimetallic strip. Bimetallic strip, where you have two metals, maybe joined end to end, where expansion and contraction is needed for the operation of that equipment, making use of this bimetallic strip. A good example is in the balance wheel of a watch. We also have it in the regulator of iron fan, of a pressing iron. We have all this in thermostat as well too. And one thermometer like that. Are you following? In all those areas, those are application. Are you following? Or application, or you talk about advantage of bimetallic strip. And bimetallic strip is one effect of thermal expansion. But the application of that bimetallic strip is an advantage. The consequence of that bimetallic strip is an advantage. So I have mentioned some areas in which you make use of that bimetallic strip. Let's see what we have here as options. I'll tell you the question again. Thermal expansion of solid is an advantage in A, fitting tires on wheels. B, construction of large bridges. C, construction of steel rail lines. D, balance wheel of a watch. And that is what I am going for. Balance wheel of a watch. Balance wheel of what? A watch. I've just talked about that because there our wristwatch makes use of bimetallic strip. The balancing of that wheel due to expansion and contraction makes it possible for time to be maintained. Otherwise, there might be a kind of lagging of time, and or maybe time being fast. During the hot period or hot season, that thing expands. And when it is cold, it contracts, thereby regulating time effectively. So the correct option is option D. Balance wheel of a watch. That is an advantage of thermal expansion of solid. So question number 7, I can just write option D. Advantage of thermal expansion. Is seen in balance wheel of a watch. All right, we are moving on to question number 8. Take note, the other ones are all disadvantages. Yeah, when railway track is being constructed, is it expected for it to expand, contract? If it expand and maybe a train is passing through, the tire, that I think that's what I can call it, you know, there is this thing that train uses to clip that railway track. So if there's an expansion, that train tire or whatever is being called, I can't remember that, cannot clip that railway line effectively. It can cause the train to slip off, thereby leading to its falling. So it's not an advantage in that case. All right, we are moving on, please, to the next question as we try to close up our class for today. All right. Question number 8. Which of the following is an advantage of expansion in metals? Which of the following is an advantage of expansion in metals? A. Bimetallic strip. B. Compensated wheel of a watch. C. Temperature control in an electric iron. D. Sagging of telegraph wire. Which of the following is an application, rather not expansion? Which of the following is an application of expansion in metals? A. Bimetallic strip. B. Compensated wheel of a watch. C. Temperature control in an electric iron. D. Sagging of telegraph wire. The correct answer is in bimetallic strip. It is an application of expansion in metals. Why is bimetallic strip the answer? That is the answer because option B and C, they fall under application of bimetallic strip. Is that okay? Option B that said compensated wheel of a watch. I just explained that. How the strip, metal strip of the watch, you know, your watch, I think that is it analog, not digital, because digital is the one that comes analog, that one that tells us has 2 needles. Those are bimetallic strips. So like the minute and the hour needle or pointer. They can expand and contract, helping in the in compensating for time during hot period and cold period. So that compensated wheel of a watch is an application of bimetallic strip, which is option A. Option C, which is temperature control in an electric iron, that also is an application of bimetallic strip. It means that B and C, they fall under option A. Option D is a disadvantage, is a consequence. Sagging of telegraph wire is a consequence, a disadvantage of expansion. So which of the following is not an application? Seems like I misread the question. Because the applications, like I said, bimetallic strip is an application. Under bimetallic strip, that's where you talk about a compensated wheel of a watch. That's where you talk about temperature control or regulator on iron. So let me read the question again, please, so that I don't say something else. Which of the following is not, the emphasis is not, an application of expansion in metals? A. Bimetallic strip. It is an application, so it's part of the application. B. Compensated wheel of a watch. It is an application. C. Temperature control in an electric iron is an application. Sagging of telegraph wire is not an application. That one is a disadvantage. Is a consequence of thermal expansion. Okay, so the correct option there is D, which is sagging of telegraph wire. That is not an application of thermal expansion. Rather, that guy is a disadvantage. Option I told you, they are applications. Question number 9. Second to the last question of our analysis. With this, we've done justice to, calculation aspect and non-calculation aspect of thermal expansion. And that is interesting. Which of the following cannot be used measure of degree of expansion in solids. Which of the following cannot be used as a measure of degree of expansion in solids? A. Linear expansivity. That can be used. B. Cubic expansivity. That can be used. C. Area expansivity. That can be used. D. Apparent expansivity. That is not used, because in that case, it's not maybe the metal already that is expanded. In apparent expansivity, you have a liquid there where the vessel is expanding alongside the liquid that it contains, right? When you hit a liquid and then the vessel expands. We are looking at a situation where you hit that solid directly. So which of the following cannot be used as a measure of degree of expansion in solids? Apparent expansivity cannot be used, because that one brings in liquid. Like I said, it's when you are hitting the liquid will not be causing the expansion of the containing vessel. That's what apparent expansivity is all about. So that one cannot be used as a measure of degree in expansion of solids. Question 9. Correct option is D. Apparent expansivity. Apparent expansivity cannot be used as a measure of degree of expansion in solids. The first three options can be used: linear expansivity, area expansivity, and cubic expansivity or volume expansivity. As a matter of fact, it is these three parameters, these three expansions that we deal with when we want to study the expansion of solid: linear, area, and cubic expansivity. So these three can be used as a measure of degree of expansion of a solid. But apparent expansivity cannot be used. You don't have any specific formula of apparent expansivity that brings in the concept of a temperature rise. You don't. Apparent expansivity is simply cubic expansivity minus real expansivity. All right, let us move on. The last question, number 10, as we conclude our class for today. And I hope you've learned something cool from this live class. I told you that I'm going to break a news to you. And the news is, going forward, at least within the time being, within the next 1 month, by the special grace of God, our helper Jehovah, GMAETS 41 will be holding live classes, possibly daily, right? Or at least 4 times a week. You want to know more about the classes, send a message to this number on WhatsApp. Request to be added to our WhatsApp group, so that once I give the update of the class, you follow up immediately. No time to waste. So you don't join late. If you join late, remember in life, there are things we've covered so far, and then you might not be able to follow up fully. Question number 10. So what we have here, the density of a liquid is 7.00 times 10 to the power of 3 kilogram per cubic meter. The density of a liquid is 7.00 times 10 to the power of 3 kilogram per cubic meter at 10 degrees centigrade. Find its density at 100 degrees centigrade. Find its density at 100 degrees centigrade. If the cubic expansivity of the liquid is 6.5 times 10 to the power of minus 5. 6.5 times 10 to the power of minus 5 per Kelvin. This particular question, I can't remember having encountered a question where something is solved with density. So perhaps this is my first time of meeting a question like this. But the truth is, I don't really care whether it is my first or second or last time. I always believe in something. you are exposed to a question, what you do is to use the knowledge of the known to attack the unknown. It's not as if this question is somehow, some way like out of the blue. No, it's still within the range. Besides, they gave us the density, initial density. The answer we should find the final density. What I'm trying to say is that I've not really seen a particular question of this kind where the problem was given in terms of density. But like I said, I'm going to use the knowledge of the known to attack the unknown. Good enough, we're given the cubic expansivity of the liquid. So, and I know that there is a relationship between volume and density to mass. Density is mass divided by volume. So I'm going to use that knowledge, then use the formula of cubic expansivity to solve this. This is what I'm going to do here. The density of the liquid at 10 degrees centigrade was given as, let's say, density 1, 7.00 times 10 to the power of 3 kilogram cubic meter. This occurred at initial temperature θ1 of 10 degrees centigrade. There is a reason why I needed to be open to you that I have not solved rather any question that is density related in terms of where the question was presented in this way. I'm not talking of relative density problem. I've solved question on relative density problem before. But this one where a cubic expansivity value is given, and then instead of volume, density was given. And mass of the substance was not given to us. If the mass was given, I could have used the formula, okay, density equal to mass over volume. Make volume subject to the formula and then calculate volume rather by dividing the mass by the what? Density. But I have no choice. That's what I'm going to do. I have to say this now. You see, I'm trying to use the knowledge of the known to deal with the unknown. So the same thing applies to you. Whenever you're exposed to an exam problem, an exam question, don't be too scared or worried. When you see something, say, I've not seen something like this before, but you know that you found that a thing is related to something you know previously. Apply the knowledge of the known to the unknown. Now, from this guy, I can get the V1 from here. I can get V1, but let's look at this. We're given find its density. The final density we don't know at the temperature θ2, which is 100 degrees centigrade. Now we are giving the cubic expansivity of the liquid. Cubic expansivity of the liquid gamma is equal to 6.5 times 10 to the power of minus 5 per Kelvin. Right? Minus 5 per Kelvin. Now, listen to the options provided. I'm going to be fast in dictating the option. Option A, 7.82 times 10 to the power of minus 3 kilogram per cubic meter. 7.82 times 10 to the power of minus 3 kilogram per cubic meter. Option B, 6.96 times 10 to the power of minus 3 kilogram per cubic meter. 6.96 times 10 to the power of minus 3 kilogram per cubic meter. Option C, 7.08 times 10 to the power of 3 kilogram per cubic meter. Option C, 7.08 times 10 to the power of 3 kilogram per cubic meter. And then option D, 7.00 times 10 to the power of 3 kilogram per cubic meter. These are the options provided. I hope this thing did not cut off from the screen. That's good. It is there. Now we are moving on to solve this question. What is this person saying? Most Nigerian accent ever. Most Nigerian accent ever. I really don't understand. Not Segnegar, right? Is it that you like my accent? Or you don't like it? Anyway, let's move on. In either case, manage my accent. I'm trying enough to ensure that everybody learns. Where are we? So this is what I want to do. I'm going to use the volume expansivity formula, which is V2 minus V1 all over V1 times change in temperature. All right, this is the formula I'm going to use. And then we are looking for, what we are looking for is not here. But of course, that thing is connected to V2. It is connected to what I said, V2. And I don't know. Can can I just say, okay, let me use cubic expansivity equal to density 2 minus density 1 divided by density 1 times change in temperature. Can I do that? I have never seen where density was linked directly to cubic expansivity. So I am going to forcefully convert this density given to what? To volume. Knowing that for this particular solid, this guy that was heated, did they mention a material? The density of a liquid, okay, they mentioned that it's a liquid. Knowing that it is the same liquid, therefore the mass is the same. The mass is the same. So whatever value I'm giving to the mass, if I want to calculate, let me say density 2 is equal to mass 2 divided by volume 2, so that V2 will be equal to mass 2 all over density 2. Then I'll divide the mass by density 2. The same way, similarly, I can write that V1 is equal to mass 1 divided by density 1. But take note, for this particular question, mass 1 and mass 2, are they different? Are they different? They are not. Mass 1 is equal to mass 2. Because we are talking about a liquid, and it is the same liquid, the masses must be the same. There is no statement in the question that shows that the masses are different. The mass of the liquid is just a single liquid given to you that was being heated, under this condition. So you can assume any value for the mass. And in a case like this, it is best to assume 1 for the mass. Let the mass be 1 kilogram. If the mass is 1 kilogram, let M equals 1 kilogram. If you assume any value for the mass and you solve, you still get the same value. So with this, I'm going to convert density 1 to volume 1 so that I can now solve and get V2. Once I get V2, I'll now convert it to what? Density 2. I don't know if I'm communicating in any sense. I'm going to use this analysis here to change the initial density to initial volume. So I can be able to substitute for this V1 in this equation, because what I know very well is that this equation is what links to cubic expansivity given to us. Once I use this formula to get V1 from density 1 given to me, I will solve for V2. And once I get V2, I'll now use this formula and get density 2. So we go. Let M equal to 1 kilogram. The implication is that V1 will now be equal to M1 divided by density 1, or simply M over density 1. I've told you that M1 is equal to M2 and is equal to simply mass because it is the same liquid you're talking about. Now this means that V1 will now be equal to 1 divided by the density 1, and density 1 is 7. I don't like that 0.00. This is significant. It's the same as 7 times 10 to the power of 3. So we are going to have 1 divided by 7, and then this 10 to the power 3 will move up. 1 over 7, what will it give to us? It's going to give us 0 naught. And because 7 cannot, if you say 1 divided by 7, it is 0 times. 1 will still be remaining because the 1 was not divided. What do you do with the 1 now? 0, put point, attach 0 to the back of the 1, you get 10. 7 can go into 10 how many times? 1 time. Remainder what? 3. 7 can divide 10 only once. The remainder will be 3. What do you do to the remainder 3? Attach 0 to it, you get 30. Divide that 30 by 7. 7 can go into 30 how many times? 4 times. Remainder 2. That 4 times is 28. Remainder 2, attach 0 to the 2, you get 20. 7 can divide 20 how many times? I think that's just 2 times. So this will be 0.142. So no need. That 2, you round it down. So this is 0.14 times 10 to the power of 3. Eventually, our V1 becomes 1.4 times 10 to the power of 2. You move the point once to the right, so you subtract 1 from this power. This is going to be cubic, okay? It's not cubic centimeter. It's going to be cubic meter. Cubic meter because the density is in per cubic meter. So the volume is now going to be cubic meter. All right. I'm sorry, I'll have to wipe this. So you take a look at it. I have to wipe to give space, all right, for further calculation here. I am set to calculate V2 now. So substituting into this formula, it implies that in place of cubic expansivity, I have 6.5 times 10 to the power of minus 5, equal to V2, we don't know, minus V1. V1 is 1.4 times 10 to the power of 2. Divide this by V1. That's a 1.4 times 10 to the power of 2. And then we're going to multiply by temperature change. the liquid was heated from 10 degrees to 100 degrees, so the temperature change is going to be 90. V2 minus 1.4 times 10 to the power of 2 is going to be equal to, we shall multiply these terms together. We don't have enough time to go multiplying this. I'm going to reach out for my calculator now. I've tried, I've tried doing a lot of work without calculator. So I shall use a calculator. And we'll see what we can do there, right? And in fact, let me see. Good. I've got my calculator, but this is what I'm going to do. I'll multiply 6.5 by 1.4, then times 90. Once I am done, I'll multiply by 10 raised to the power minus 5 times 10 raised to the power 2. I shall use indices law there. That is what I've been saying. And if you are allowed to use normal scientific calculator, per se, maybe say in JAM, there's nothing wrong with that. I'm still emphasizing on it seriously so that our organ at the tops, right, the JAM officials, they have to look into that, because even they themselves, I don't know how many JAM officials can be given such question like that in exam, subjected to such situation that might thrive normally. We just have to be honest. It's not all about we have opportunity of giving questions to people and then we do whatever we want to do. The same statement goes to all examiners and educators. If you are working in schools, know the kind of conditions you impose on students. So 6.5 times 1.4 times 90, this gave me 819, then times, this is 10 raised to the power minus 5, this is 10 raised to the power 2, add the powers, you get 10 raised to the power minus 3. While I am talking about the officials that conduct examinations, I'm talking about teachers in schools, take note to students, that doesn't mean that you should not relax. Say everything you carry calculator. You see 50 minus 27.1, you carry calculator. You see 100 times 20, you carry calculator. Come on. That is unfair. It's unfair to you yourself. We are moving on. Make V2 subject of the formula, and then you are moving 1.4 times 10 to the power of 2 to the right. So it's going to be 819 times 10 to the power of minus 3. All right. You know I got the minus 3, minus 5 plus 2 using multiplication law of indices. Then plus 1.4 times 10 to the power of 2. Our V2 will now be equal to, remember, for you to add up this, the 10 raised to power, 10 raised to power, they must be in the same power. The power of 10 must be what? The same before you can add. So I'm looking at this. It is either you convert minus 3 as power to plus 2 as power, or you convert plus 2 as power to minus 3 as power. I've done something like that in previous question. Right? I've done something like that in previous questions. So we can be guided by that to do so. Let me see the options given. That will help me to know how likely I might want to present my options. Now the powers are in power minus 3. All the powers given in the options, they are 10 raised to the power minus 3. 10 raised to the power minus 3. So I'll be guided in that. It means I'm going to convert this to 10 raised to the power minus 3. I'm going to convert this to 10 raised to the power minus 3. Let's do that. To convert it, what can you do to 2 to get minus 3? What can you do to 2 to get minus 3? Definitely it is to subtract 5. If you subtract 5 from 2, you get minus 3. 2 minus 5 is equal to minus 3. And that will make the power of 10 to be the same as the power of 10 here. Therefore, but how do you now subtract 5 from these 2? Do you just go and then minus 5, you start solving? No. You move your point 5 times to the right here. 1.4. Let's do it together. So have 1.4, move your point 1, 2, 3, 4, and 5. So we find out this becomes 1, 4. Here is 0. Here is 0. Here is 0. Here is 0. 1, 2, 3, 4. 1, 2, 3, 4. Then you have your point at the back. So you say this is 140,000. It means if I convert 1.4 to 140,000, the power of this will now become 10 raised to the power minus 3. So let me wipe this. And then do that, 140,000. So this is going to be, let me show that so we don't waste our time. This term you are seeing here is going to be 140,000 times 10 to the power of minus 3. I've done the conversion. And so you'll be adding 819 to 140,000. And how do you do the addition? It's simple. 9 plus 0 here is going to give you 9. 1 plus 0 is 1. 8 plus 0 is 8. You know, in terms of 100 times a unit, do your addition. So this is going to be 140,819 times 10 to the power of minus 3. This is what I obtained here. This is what I obtained here. So my V2 is this value, 140,819. But the question we're asked to find, it is not volume that we're looking for. We have to find the final density. Therefore, the final density is going to be, remember, density is mass over volume. So it's going to be the mass divided by the volume, V2. And that's going to be the mass, we assume 1 kilogram for it. I've told you whatever value you use. And they're going to divide it by whatever value you use as mass, you get the same answer at the end. 140,819 times 10 to the power of minus 3. This will definitely go up, you know. So let's divide 1 by 140,819. 1 divided by 140,819. So it gave 7. This is equal to 7.1. 7.1. Then this 10 raised to power minus 3 would go up, you know. It becomes times 10 raised to power 3 positive. The unit will now be kilogram per cubic meter. This, of course, is the final density of the liquid at this 100-degree. I'm done solving this question. And that is that. The options I have here, I have option A, 7.82 times 10 to the power of minus 3 kilogram per cubic meter. That is not the answer. This is 7.1. And in fact, the power is 10 raised to the power 3, not minus 3 as we have here. Option B is 6.96, because that's not the answer, because it's not agreeing with what I have here, 7 point something, 7.1. Option C is 7.08. 7.08 times 10 to the power of 3 kilogram per cubic meter. 7.08 times 10 to the power of 3 kilogram per cubic meter. And then option D said 7.00 times 10 to the power of 3 kilogram per cubic meter. Now, you see this option C and D. These two guys can pose a threat to a student, say you're seated in an examination hall. You see these two options, they are approximately equal. Option C, 7.08. Option D, 7.00. Both of them is times 10 raised to the power 3, just like we have here. So which of them is the correct answer? Is it 7.08 or 7.00? Because like I said, both of them are approximately equal. Now the correct answer will be option C, 7.08. Why? This is because the options are presented in 2 decimals. The options are presented in what I said, 2 decimals. No. It's 7.08. When I press this is 7.10. No, there's no 8 there. I'm sorry about that. What I have here is actually 7.101, you know. Come down. 1 divided by 140,819. What I have here is 7.101 times 10 to the power of minus 6. Times 10 to the power of minus 6. So this thing has 10 raised to the power minus 6 here. This 1 over this. Please let me wipe this and write it correctly. I did not take note of the 10 raised to the power minus 6. 1 over this 140,819 alone is 7.1013. Let me write out everything. Then times 10 to the power of, now watch, 1 over this alone produced 10 raised to the power minus 6. That's what it produced. But remember that there is a 10 raised to the power minus 3 under. If it goes up, it will become positive. It will become what? Positive. Which according to multiplication law of indices, you're going to get something like this. Okay. So this is what we are going to get in effect. 7 point into decimal. This is going to be 00, then times 10 to the power of minus 6. And then plus 3 will give you minus 3. Kilogram cubic meter. So this is actually what I arrived at. All right. Which goes with option D. Which goes with option D. 7.00 times 10 to the power of 3. But I'm assuming it's supposed to be minus 3 anyway. I'm reading exactly what we have in the question as students provided. The first two options is 10 raised by minus 3, 10 raised by minus 3. Then the last two options, 10 raised by 3, 10 raised by 3. But I assume it's meant to be 10 raised by minus 3 anyway, based on what we've solved here. So if I were to be in the examination hall, I would go with option D, 7.00 times 10 raised to power minus 3 up, that power 3 there. Why will I go with that? The options were given in 2 decimal places. If you go with option C, which is 7.08, if you approximate to 1 decimal here, you will get 7.1, which is the same as approximating this to 1 decimal. But the options given there are in 2 decimal. So your examiner wants you to respect that these guys are in 2 decimal. And if you approximate this to 2 decimal, then that's 00. Are you following, right? 10 raised to power minus 3. So that is that for these 10 questions provided by the GMAETS 41's physical jam lesson student. The venue of our lesson is at IDK, Jam and WAEC lessons, right? So you can always visit us if you're in Oka, Anambra State, to join us. However, you can always link up online, you know, just like you have this wonderful class. And don't forget to become a channel member. To do this, you click on the Join tab on the GMAETS 41's channel. Alternatively, in the comment box or comment section of this particular live stream, you have the currency icon by your right. You can click on it, all right, and support GMAETS 41 with whatever that is convenient for you. I hope you learned something from this particular class, and that is that about thermal expansion. Tomorrow, I am going to be taking you on the concept of all this heat energy. Are you following, right? Heat energy, where we deal with specific heat capacity and latent heat of fusion. We are going to deal with that aspect tomorrow. Make sure that you are around by the hour of 6:30 p.m. I am going to kick off that 6:30 p.m. Nigerian time. Are you getting me right? So make sure that you connect to the class. Queen Oma, thank you very much. Omi, is this JAM class? Yes, JAM and WAEC, SS1, SS2. I want to advise you guys, please. You hear all this thing, you hear JAM, WAEC, as if these people are setting different kind of questions. Please, always bear this in mind. Even SS1 students. Think, for example, thermal expansion is an SS1 topic. So an SS1 student can connect to this class live and learn to benefit. Even if it's an SS3 topic, for example, an SS1 student can learn it. What is there? This is as simple. Anybody can follow through. All right? But what was done here actually, okay, if we are to classify it, we say JAM and WAEC class, all right? But this platform covers all levels of education. So, Ami, you're welcome. Damn, I missed this. I'm taking JAM this year. Relax, Ami, okay? Just relax. Your welcome is good. You've seen this platform. This is GMAETS 41, a platform 100% committed to giving students the best. At the end of this lesson, at the end of all our live streams, a copy of the lesson will be made available on this channel. So you can slide through into GMAETS 41's main channel. How do you go to the main channel? Click on any of the GMAETS 41's video. Then just below you see the GMAETS 41 blue logo where you have G41 there. click on that blue logo. It will run you straight to the GMAETS 41's main channel where you see only GMAETS 41's works. You can click on playlists. You can click on live. All our live video lessons are grouped under live there. If you click on playlists, you will see, like I said, academic wonders for you, dear friends. Thank you for coming to join the class. My physics score last year was terrible. Don't worry, you can upgrade it this year. Can upgrade it this year from this platform. To be honest, because I am committed to carrying you, I'll be running classes regularly: physics, chemistry, math, English. If you follow all the trades, you can smash 90s and up to 100 even. It's possible. Who said that a student cannot score 100 in a particular subject? A student can actually blast 100. Yeah, it is highly possible. And this platform is committed to giving you guys the best. So make sure, share this lesson to your friends. Are you following? Don't worry, I mean, you will get above 58 this time around. At least, thank God you've been able to link up with this channel. You've been able to link up with this channel, follow up with the classes. We have lots of video lessons on this channel to guide you. Physics, chemistry, maths, English. GMAETS 41 has a special channel for English. You can type GMAETS, basic class. For that English, because I consider English as a language subject, something that all levels of learning can deal with, all scholars. So I have a special channel, the GMAETS 41's channel for basic level of learning. All of our English stuff, they take place there. Now, I want to say this place to the GMAETS 41's dear student, and of course to you guys taking JAMB as well to WAEC. Are you following, right? SS1, SS2 student. Tomorrow morning, by the hour of 7:38, I'm going to run a live class on English. There is this English, class that I'm still owing. Our JAMB students, physical lesson JAMB students, they are aware of this. We are supposed to do a revision on oral English part, consonants, because we've treated that. Questions are already available, sent by the GMAETS 41's Group 1 Arts class, right? We're going to review that. At least let me be done with that, though that I've paid that. 7 o'clock. So for the GMAETS 41's physical class students, right? Before you come for the JAMB lesson, for the WAEC lesson, which is by 10:30, I guess tomorrow you have biology. In the morning, you can do something. You can activate your brain before you enter the class for biology by 10:30. Okay? So 7 o'clock a.m., you're going to have, at least within 30 minutes, we should be done with the consonant questions or problems that have been sent to our WhatsApp group. Okay, so make sure you stick around tomorrow morning by 8 a.m. The class is going to be 8 a.m. to 8:30 or 8:45 a.m. So we are done with this, like I said, and this topic is on thermal expansion. Share this lesson, please, to your friends, and then invite them to subscribe to this channel. Encourage them to become a channel member also. And then make sure you follow up with our classes. Don't always wait only for live classes, please. GMAETS 41 has so many video lessons. Are you following, right? That you can take at your convenience, which are not live. Like I said, go to the channel. And to go to the channel, just click on the GMAETS 41's icon and the logo. It's blue. Click on it to take you to the channel, and then you can see lots of video lessons to take there. All right, guys. You said 7 o'clock, right? Now, I think let's make it 8 o'clock, because I'd like to sleep well, at least. Maybe 8 o'clock. I really need to sleep. People that have been following GMAETS 41 online can tell you the stress I've been through just within 2 weeks now. So please, it's going to be 8 o'clock. I'm sorry. And being a live class and online, anybody, you can stream from anywhere at any time. So try to arrange your this thing. When I rest well, I really need to rest well within this week also. Then we can make the class a bit earlier, because I know that by 8, a lot of people will be running for the activities and other things. Can make the class maybe 6 a.m. Are you following, right? And stuff like that. I have a lot of one-off package for you guys, like I said, right? Just pray for life and strong health, and I will always be there for you guys. Please do take a wonderful time and take good care of yourself. All right, have a good night rest, and dream well and dream of what we've learned. Don't dream any other thing where you are. Dream about what we've learned, right? Love you guys. To have a wonderful night rest. From here, this is GMAETS 41.